Hi, everyone. I've had several introductions here and my picture put up and everything, so thank you for all that. And thank you for Aaron for letting me speak here in this position. So I'm a relatively new faculty member, like the list of, you saw me on the list of new faculty members around. And we're still towards the end, let's say, of building our new lab. It's a superconducting qubits lab. And this is what I want to talk to you about today, about the field of superconducting quantum circuits. Well, let me start with what are superconducting circuits and what they're related to. And this field is quite hyped, really. I mean, if you go to Google and you look for quantum computer, this is literally just a screenshot of what you would get if you search for quantum computer. And what do we see here? Pictures of? Anyone? Dilution refrigerators. Okay, so you search for a quantum computer and you see loads of dilution, and you've got to scroll pretty much down there to find something that is not a picture of a dilution refrigerator. Now, these pictures are so pretty and so nice and so related to quantum computing, they even appear, you know, on the cover of the Technion President's Report. There's a dilution refrigerator. That's the one from our lab. Now, what these pictures of dilution refrigerators tell me, or at least tell me in the context when I'm searching for a quantum computer, is that this field is overhyped. And there's a lot of popularity, and there's probably a lot of misinformation. Okay? So what I would like to do in this talk is try to strip away all the hype and give you an easy introduction to what these circuits look like, how they operate at the very basic level. And then towards the end, I will talk about what we do in our lab. Okay? So this is our plan for today. Okay, so this is what the lab looks like. And in general, what this field is, what we do with these circuits, so we build these circuits. These circuits lie on substrates, just like regular fabrication, silicon or sapphire substrates. And these are electrical circuits that are designed to work in the gigahertz range, typically 4 to 8 gigahertz. That is a comfortable band, but can be extended to 2 to 20 gigahertz. These circuits are cooled down to millikelvin temperatures, far below the gigahertz range. And this is where the nice pictures of the dilution refrigerators come in. They're just used to cool down these circuits. And the sizes of these circuits range from tens of nanometers, so this is like 100 nanometer, all the way up to millimeter in size. Okay, so this is what we're looking at. We're looking at gigahertz frequencies, millikelvin temperatures, and nanometer to millimeter size circuits. Okay, so this is all we're talking about. And you have to fabricate them, make them, mount them inside the dilution refrigerator, put them inside, and measure them with standard microwave electronics. Okay, so this is what a lab looks like. Now, we are talking about quantum circuits, and what I want to explain now is what really makes this quantum. Why are these quantum circuits? And usually when we think about quantum, we think about real microscopic things, you know, atoms and so on and so on. And really, this field of superconducting quantum circuits has a different name. The name I prefer, circuit QED. Now, the circuit QED is named after the field of cavity QED. Okay? Now, this field of cavity QED, pioneered by Serge Haroche and Dave Wineland, received the Nobel Prize in 2012. And in this field, they take real atoms, okay, with real quantized energy levels, okay, and they put them in cavities, okay, to show control. Okay, and this was tremendous work with beautiful, beautiful data. And what we do in the field of superconducting circuits, in a sense, mimics that field. Okay, we take elements, capacitors, inductors, and an additional element called Josephson Junction, and we build these little circuits. They're made out of macroscopic number of atoms, so 10 to the 23 atoms. But these 10 to the 23 atoms mimic real atoms. They mimic in the sense that you have quantized energy levels, which are not equally spaced. Okay? So these are kind of artificial atoms from these circuits. And then just like in cavity QED, we take these atoms and we put them in cavities to isolate them from the environment and to help us control them. So we take these circuits and we put them inside cavities. Okay? So how do you get a quantized system from an actual circuit? Okay, so you take circuits every day. They don't behave in a quantum way. Okay. And the simplest circuit we can think of, and we're familiar with, is the LC resonator. Okay, so take an LC resonator. You've all took it at some point in your life, and you saw that it has a nice resonance. Okay, and if you go to a quantum class, you can actually quantize a circuit, and you see that it behaves like a harmonic oscillator. Okay, so we have a resonance. There's a harmonic oscillator. If we cool it down enough, it will be a quantum harmonic oscillator. Now, this is not an atom, right? To get an atom, to get some two-level system, we need some nonlinear system, like a real atom, where we can take out two energy levels and use them as our quantum bit. And to do this, we use an element called a Josephson Junction, which is simply a sandwich of a superconductor, insulator, superconductor. And to those who are not familiar, you can just think of this element as another circuit element. You have capacitors, inductors. We don't really have resistors because we're working with superconductors, so we eliminate dissipation that way. But we can think of this Josephson junction as a nonlinear inductor, okay? An inductor that depends on the current. And that is what breaks the harmonicity of the harmonic oscillator. And if we think of the circuits in this way, then we can plot, we can think of our circuit in a, we can place them in a kind of periodic table structure where we can play around with the circuit elements. So we have capacitors, the shunting junctions here, think of them as very large inductors, and our Josephson junction. And we can play around with these circuits to build different circuits, and they will give us different energy levels. So the x-axis here is some potential, some parameter, and this are the energy levels. And here, as we go along this axis, we're just adding shunting junctions, and here we're adding shunting capacitance over here to these circuits. And we can go around and play with these elements and print them however we want on the substrate to get all kinds of types of artificial atoms. Okay? And this is basically kind of the field. And you can see the progression through the years. They kind of play around. You don't typically hear about all of these circuits. The circuit that you typically hear about, and the circuit that prominently almost everybody uses and talks about, is this guy over here. It is called the transmon. Okay? It is the simplest circuit to fabricate. It is the simplest circuit to use, and it is highly coherent. Okay? So this is usually what everyone talks about, and this is what I'm going to show you today. Okay? So when you hear about IBM, Google, whatever, most research groups, this is what they use. They use this circuit. And the idea of the circuit is pretty simple. If you think about the LC resonator, if you replace the inductor with the Josephson junction, okay, then you get the slight unharmonicity, and then suddenly our energy levels are no longer equally spaced. We get slightly negative unharmonicity, and then we can treat the two lowest levels as our qubit. Okay? And the circuit is designed such that in the gigahertz range, around half a Kelvin, and we cool down our circuits to 10 millikelvin, so that's far below, so most of the time we're just in the ground state if we let the system sit there. So what does this look like? So this is a qubit from our lab. What you're seeing here, so this is an aluminum box. Okay? If you take a box, quantize, you get electromagnetic field inside. Okay? So this is the green thing, that's the electromagnetic field. And here in the middle, this is a silicon substrate. And on the silicon substrate, you can see these two little squares. These are aluminum squares. These are the capacitor for that transmon. And in between here, you can't see, there's a little wire, and in the middle of the wire, there's a Josephson junction. Okay? So we have a Josephson junction capacitively shunted by a capacitor over here, and the shape of these antennas makes a little dipole that couples to the electromagnetic field. Okay? So we have our artificial atom coupling to an electromagnetic field, just like in the QED setup. And this can be described nicely by the following Hamiltonian. So this is our qubit term. This is our harmonic oscillator term. This is our cavity mode over here. And this is our Jaynes-Cummings interaction. Now, typically, these circuits are operated in the regime where the resonator is far detuned from the qubit, like so. And then we can do second-order perturbation theory. And this interaction term turns into this dispersive interaction, which just shows us that the frequency of the harmonic oscillator depends on the state of the qubit. And this is our circuits. Now, what I showed you now is called the 3D architecture. There is a different architecture, which is maybe more popular in the industry, and it's called the planar architecture. So what you're seeing here is a 10-qubit chip. Remember the two little ears, the two little the capacitor? These two little things, this is the qubit. These play the capacitor. This is a 10 millimeter by 10 millimeter chip. Okay. The green stuff over here, that's niobium. That's also a superconductor. And over here, you can see the two squares of the qubit. There's a little line over here, and in the middle is the Josephson Junction. So that's that same trans one. And this black line over here, that plays the role of that big box, that big aluminum box. That is a harmonic oscillator. It is a coplanar waveguide. Okay? And you can see here there are 10 qubits over here sitting on this chip. Okay? And each qubit has its own harmonic oscillator. Okay? And well, these 5 qubits are all alone, separated from each other, but these ones also have harmonic oscillators coupling them. So these are their couplers. They couple. So you have 5 qubits which are coupled to each other over here, and 5 qubits which are isolated. And here we have a transmission line. The transmission line here is just used basically to talk to the harmonic oscillators. It has the same role of this pin over here. You see this little pin antenna? That's where you inject microwave tones and see them get reflected. Okay? So this transmission line plays basically the same role. Okay? But it's the same system. Questions up to here? All right. Okay.
Is it good or bad that the qubits are different? Each one is different from the other.
Oh, these? Well, that depends what you want. But in general, you don't want them to be identical. Right? You do want them to be different. Okay. So to this whole story of atoms in the cavities, we want to add a very important element, and this is quantum limited amplification. So what I'm showing you here is our main tool for reading out the signals from the fridge. So this is an amplifier. Now this amplifier is basically, it's a circuit. This is a capacitor, inductor, and 2 squids over here. So these are Josephson junctions. And this is also a slightly nonlinear circuit. If you're familiar with amplifier, you can think of this as, this is, for the optics people, this is an optical parametric amplifier. It behaves in a similar way. Or you can think of it as a Duffing nonlinear oscillator. But at the bottom line, these amplifiers, they provide us with above 20 dB of gain, okay? And quantum efficiencies of about 50%, and they amplify the electromagnetic field for us. Okay? So once we have all these elements, what do we do with them? Okay? So this is a mock setup. Okay? So here you can see our qubit. It is in a cavity. Okay? The output of the cavity is connected through isolators to our amplifier. And what happens in an experiment is that we send in microwaves in through the antenna port over here. These microwaves interact with the qubit over here with our system. They come out, they get routed to the amplifier, which amplifies the signal, and we can read it out. Now, if we typically work in this regime, see, where the qubit and the resonator are far detuned from each other. Now, if we send in microwaves on resonance with our qubit, just like an atom, we can excite it from ground to exciter to get full control over, over the Bloch sphere. If we send in microwaves on resonance with the cavity frequency, okay, note that due to the interaction, okay, we can think of our Hamiltonian as, this is a Hamiltonian for the qubit, and this is the part for the harmonic oscillator. So we have a harmonic oscillator whose frequency depends on the state of the qubit. So we can think of it as we have 2 resonance frequencies, and if the qubit is in the ground state, this is the resonance frequency. If it's in the excited state, this is the resonance frequency. And what we do is we inject a sine wave, a coherent tone, right at the resonance frequency of the harmonic oscillator. Okay? And we measure the reflected signal. Okay? And according to the reflection, we know if our qubit is in the ground or the excited state. Now what happens is we're sending in this microwave signal. It gets amplified. It comes out to room temperature. We mix it down. And what we see at the end of the day is the voltage is a function of time. So it just looks like a lot of noise. And if we average this noise for a long enough time, we'll get a result which is either 0 or 1. Okay? And this is how we read the qubit. Okay? And these are the basic elements of how you use these superconducting circuits. Okay? So to summarize what I said up till now, we have these nice circuits. We put them in cavities. If we send in microwaves at the qubit frequency, we can get full qubit control. If we send in microwaves at the cavity frequency, we can get qubit readout. Okay? And this is the basic operation of these circuits. Okay? And then, of course, we can go ahead and measure, coherence times, decay times, characterize them, and so on and so on. But instead of going on into details of what they do with multi-qubit chips and so on, I'd like to take the last, how much do I have? 4 minutes? 5 minutes? Okay, great. To tell you what we're doing in our lab. Okay? So you'll understand the paradigm of trying to build a quantum computer and so on and so on. One of the projects that we have in our lab is encoding quantum information in multimode cavities. So the idea here is to switch the paradigm of, instead of encoding our information inside the superconducting qubits, we're taking our qubits and using them to control the electromagnetic field in the cavity. And now the information, the quantum information, is encoded inside cavity mode. So we can create all kinds of states like Fock states, cavity states, and we can manipulate those. Okay? And so we're exploring all kinds of ideas, and to explore this experimentally, we're building cavities that can hold many modes. So using a single qubit, but many electromagnetic modes, we can control those with that single transmon. Okay? Another project that we're working on is called the multi-qubit Zenogate. In this project basically comes to answer the question of, if we have 2 or n non-interacting qubits, and I only have control of 1 qubit, a local control of 1 qubit, can I create a gate between them? Can I entangle them? And the answer is yes, if I have a strong measurement in the Xena region. And maybe I'll be able to touch upon this if I have enough time. Another project that we have is some more applicative broadband amplification. We're trying to increase the bandwidth of the amplification. And we have projects including hybrid superconducting qubits over here, which I think Eyal will talk a little bit about that. No. Okay. So no one will talk about that. All right.
But there is a poster on that.
Oh, there is a poster. Okay, so please go see the poster. Okay. All right. So this is what the HiQ multimode cavities look like. But I want to use maybe my last 2 minutes to talk about the other project, the Zenogate one. Okay, which I promised you that I can create a coherent entangling gate if I have only non-local term in only a local term in my Hamiltonian. And the concept, or the abstract concept, is something that has been known for several decades, and it's the xenodynamics. And the idea is that if I have some Hamiltonian and I drive my Hamiltonian, I will get some simple evolution. Okay? If now I can observe really strongly some subspace, I'm basically asking the system, are you in the subspace, are you in the subspace, are you in the subspace? And if I do it rapidly enough, and the system started outside the subspace, the system can't jump into that subspace. And that alters the dynamics, and it can alter the dynamics in a very non-trivial way, such that we can get very complex, yet coherent evolution. Okay? And the system that we're thinking of, and that we're building, so think of a system of a few qubits. Here I have 3. And what we're going to be doing is we're going to be driving one of these qubits. These are not qubits, they're transmons. They have more than 2 levels. Okay? And we're going to observe them. Okay? And this is our computational subspace. So these are the energy levels over here. And what we're going to be doing in this protocol is we're going to be driving one of these transmons, but we're going to be driving the 2nd to 3rd level. 2 minutes. Excellent. If we drive the 2nd to 3rd level, trivially, all we're doing is we're picking up this phase over here on all these levels over here. This level takes the third qubit from 2nd to 3rd level, 2nd to 3rd level, and so on. So all these levels will pick up a trivial minus sign. Okay? However, and this is due to the interaction, and I won't go into explaining the Hamiltonian, but if you look at the Hamiltonian, and if we look at the cavity transmission of our system, it will be separated into different peaks. And each peak represents the number of total excitations in our system. So in this specific system, if we send in a very strong microwave signal over here at the n+1 qubits, at the number of excitation which corresponds to n+1 qubits, and we look at the transmission, so we're sending in microwave light on one side and looking on the other side. If we see nothing, we know that the system has not evolved into that subspace. Okay? So we're basically, by observing and seeing that the system has not evolved into it, we're blocking it. Okay? And this blocks this transition. And now, because we've blocked this transition, all these other levels are still picking up the minus sign. And now, this is no longer trivial, and we've created basically something that is equivalent to a C0 phase. Okay? And with that, I'm done. And so this is our group. And I do welcome you to come and look at our lab. And we do have openings if you're looking for a PhD. Thank you. I'll leave you time for questions.